find, today we will learn applications of Gauss's theorem. Gauss's theorem can be used to obtain electric fields due to so many charge distribution on defined shapes, like on a sphere is a defined shape, like on a plane sheet, like on a linear charge distribution. And you can find electric field in a very simple way. We will find an electric field using Coulomb's law due to these charge distributions, and that was very lengthy and that was very difficult. Now if you use Gauss's theorem, it becomes quite simple. So let us learn today how to apply Gauss's theorem to find electric field due to some charge distribution on even or uniform shape. So applications of Gauss's theorem. And first one application I am taking to find electric field. Due to charge on a hollow sphere first case outside the charge sphere, outside the sphere. Second, on the sphere. And third, so three things we have to find. Third, inside sphere. So for this, we will have to first of all draw a Gaussian surface for such charge distribution. Let the charge density be sigma. Charge is uniformly scattered on the surface. So first work, and suppose this sphere is of radius small r, and we have to find electric field at a distance capital R. We have to find electric field outside here, first case. So my first step is step 1, to draw a Gaussian surface. Passing through the point P. Point P, where we have to find electric field. Now, here is a Gaussian surface. And then, from the definition of electric flux, now, we know that electric flux phi net is equal to surface integral of E dot ds, and it is equal to charge enclosed by epsilon naught. So here it is having Q charge. Surface charge density sigma, and it is having Q charge. Okay. So you can write in terms of charge also. So let us do here. Here we have taken a sphere which is symmetrical to this charge sphere, and the distance of this sphere everywhere is r only, the radius of this Gaussian surface. and as it is having the same distance from center, so electric field which depends on distance from the charge, and it is inversely proportional to square of distance, and it is proportional to charge also. So when charge is same, distance is same, so electric field must be same all along. So here E becomes a constant, so our work becomes very simple. So this is, E is a constant, so let us take it outside. Integration of ds is equal to q enclosed, it is already q only by epsilon naught, and it implies that E into surface integral of this small surface area which we have taken. Here actually we have to take a small surface, this surface. So first step to take Gaussian surface, and at point P where we have to find electric field and select a small surface vector del S. So first step is to draw a Gaussian surface and take a small surface area on that. Suppose that surface area is of value del S vector, so this del S vector. So when you integrate the whole surface area, it will become the surface of the Gaussian surface. And that is equal to 4. Whole surface of a sphere is equal to 4 pi r square is equal to q enclosed upon epsilon naught. It implies that electric field is equal to 1 upon 4 pi epsilon naught q enclosed by r square. So this is how, in a simple way, in 4 steps you can see, in 4 steps we could find electric field due to a point charge. Now case 2, question 2, electric field on the surface. On the surface of the charged sphere. Now in this case also, we will draw a Gaussian surface that passes the surface of the sphere itself. First step, to draw a Gaussian surface passing through the charged surface itself. Okay, so we take charge surface and we draw Gaussian surface through this surface only. This is our Gaussian surface. And step 2, to have a small surface area on this Gaussian surface. To have a small surface area vector del S on the Gaussian surface. Here is your del S, and since the electric field at all the points on the surface is same, that is E, because it is at the same distance from the center, let it is at, which is we have already taken it small r, so electric field will be same. Here E is same whole on the surface. Therefore, flux phi net is equal to surface integral of E del S, and this is equal to, according to Gaussian theorem, it is equal to Q enclosed by epsilon naught, according to Gaussian theorem. Therefore, E is uniform, E is constant. We should integrate the surface area, and this is equal to 4 pi r square, and this is equal to Q enclosed by epsilon naught. It implies that E is equal to 1 by 4 pi epsilon naught Q enclosed by r square. So this is electric field on the surface itself. Now, third case, electric field inside the charged hollow sphere. So here is your charged hollow sphere of radius r having charge q, net charge q, and you have to find electric field at the point P, which is inside. Here we have to find electric field. So first step, to draw a Gaussian surface. Step 1, to draw a Gaussian surface through the point given. Step 2, second work you will do, to take a small surface vector. Let del S vector is small surface vector. Let me take small surface vector del S here. Small surface vector on the surface. Now, according to Gaussian theorem, using Gaussian theorem, flux phi net is equal to surface integral of E dot ds, and this is equal to Q enclosed by epsilon naught. Therefore, E into, suppose small surface area, Gaussian surface has radius vector S. So it is equal to 4 pi s square is equal to, and the Q enclosed is 0. Q enclosed is 0. So we can see that electric field becomes equal to 0 only. So electric field inside is equal to 0. This is how you can find electric field using a Gaussian theorem. It is a very easy way to find electric field due to charge distribution on known states. Now, if you take electric field due to linear charge density, second application, electric field due to a linear charge. Take a line charge. Suppose this charge is positive 1, having charge density. Since it is linear charge, so we can take charge density lambda is equal to charge density. Let lambda is charge density. Now here in this case, you cannot take Gaussian surface as spherical one, because if you take a spherical surface, you will have electric field at each and every point different due to different distances from this charge distribution. So this is not symmetrical surface in the case of linear charge density. For point charge, A sphere is the symmetrical surface, but for linear charge, a sphere is not symmetrical surface, and you cannot take a Gaussian surface a spherical one, because at the surface the distance from this charge distribution is different at each and every point, so it is not symmetrical surface. So let us take another surface. Here I am taking a cylindrical surface. Okay. And linear charge density is lambda. So now here we have three surfaces. We have three surfaces, 1, 2 and 3. Surface 1, 2 and 3. We have three surfaces. So we will add flux due to all three surfaces. As you know, flux is a scalar quantity, so flux net can be equal to phi1 plus phi2 plus phi3. Now let us take small area everywhere, and then we find the surface integral of flux and electric field. Here, electric field will be, due to a linear charge distribution, electric field will be perpendicular to the linear charge distribution. The direction of electric field is this one, and which is parallel to surface vector here. Del S2 is parallel to E. Del S2 is parallel to E, but if you take a surface vector at 1, del S1 is perpendicular to E. Del S3 is also perpendicular to E. So let us write flux due to all these three different surfaces. As we have three surfaces, so we add flux to all the three surfaces. So it is equal to surface integral of E dot del S1 plus surface integral of E dot del S2 plus surface integral of E dot del S3. And as we know that cos 90 is equal to 0. So this becomes 0 and this becomes 0. As cos 90 is 0, here let me write E del S1 cos 90 plus surface integral of E del S2 cos 0 plus surface integral of E, whatever E be there. I don't know what is the E over there. Let it is E1, it is E2 and it is E3. Del S3 cos 90. So the two terms become 0. Therefore, flux phi net is equal to surface integral of only net A, which is perpendicular, and at Gaussian surface it will be E net, because it is at the same distance. You can see the distance on the surface all along is same. So यहाँ पे जो इलेक्ट्रिक फील्ड है वो भी सेम होगा और उसको हम E2 is equal to E मान लेंगे. Let E2 is equal to E. Okay, so E2 is E and into surface area. So del S2 and it is equal to charge enclosed, Q enclosed by epsilon naught. Now it implies that E and surface, curved surface area is equal to a length. When you will open it out, it will be in the shape of a rectangle. So curved surface area will be equal to length into breadth, and its length will be equal to 2 pi if it is at a distance of r and its length of this cylinder is L. Let us suppose that cylinder has radius vector r and its length of the cylinder is L. So we need to take all those things. So when you open this cylindrical shape into a rectangular sheet, the length will become 2 pi r only and length also is given. This becomes equal to this